Hi, folks. Congratulations. You have now completed first order logic. You have learned and mastered the fundamental logical system, the goal of this course. Because what we've done now is we've completed all of the proof theory for FOL, the intro and elim rules for the quantifiers and the identity predicate. And that's the last thing. You have all the parts of now this major first order logical system. What we're going to do now is start to apply it in various ways and see the import and why this system is so important to learn. We've seen this trickled out throughout the quarter in various ways. For example, we've talked a little bit about how first order logic or just formal logic in general relates to the study of natural languages. And this is foundational for the philosophy of language and for the whole field of linguistics. Because what folks do in linguistics is they take natural languages like English and they study the syntax and semantics and pragmatics of those things. And what that has to do with is understanding the logical syntax of all these different parts of natural languages. And it's easy, we were able to stipulate our formal models how we wanted them to work. But this is then, linguistics is the empirical study of how English actually works and what kind of logical syntax it has, or any other natural language works, like German or Chinese or Mandarin, etc. Now, another area of application we've looked at a little bit, but we haven't delved into, is the philosophy of religion. One of the key topics, foundational topics in philosophy of religion and questions of religious belief is, are there good reasons for believing in the existence of God or some other deity or spiritual force? Can you prove that God exists or not? Are those logically good arguments? Are they valid? Are they sound? And there's been major advances in the study of philosophy of religion by looking at and formalizing some of those arguments and seeing their strengths and weaknesses. So the ability to analyze arguments rigorously has really contributed a lot to the understanding of philosophy of religion. Another area is computer science that we've talked about. Computer science, what would the 20th century be without the invention of computers? Logic was foundational to this whole project. First order logic came first in the end of the 1800s, and it was just a couple of decades later that people started to realize how this helped them understand which functions are computable or not, and they could formulate the concept of what is the computability concept itself in rigorous terms for the first time. And all of the first programming languages arose directly out of the symbolic languages in used in versions of FOL. So computability theory and all of computer science simply would not exist. It is just an outgrowth of the logic that you learn in this class. And indeed, not just the history of computability 100 years ago, but the frontiers of computability right now, and understanding quantum computers, quantum computability, and fuzzy computing. That comes out of fuzzy logic. And if you want to go on from this class and start to learn advanced logical systems, you can see how implementing those systems is precisely what people are trying to learn how to do now. And that's what a lot of interesting engineering problems arise out of. Now, that takes learning some additional logic. So what I want to talk about here is how important logic is to the foundations of mathematics and how it's related to psychology as well. I'll talk about psychology in some other videos, so let me say something about mathematics now. When you first learn mathematics, you just, like in grade school or something, you just learn how to do computations, and you just sort of, add, multiply, divide numbers. But what mathematicians do is they're not just sort of sitting around crunching numbers all day. They want to prove the results that you're relying on when you do those computations. Like, let me give you an example. When you're in grade school and learning about multiplication, you just want to first be able to compute this thing. And then at another level, or you learn these operations, like you can distribute multiplication over addition, for example. But a level of abstraction beyond this is in algebra, you start to replace these numbers with letters, with arbitrary names, or with variables. Because this distribution doesn't just hold for the numbers 2, 3, and 4. It holds for no matter what numbers you put in there. And we don't want to just take that on faith. So step one is being able to formulate this in more abstract terms by using variables, for example. But we don't want to just state that and assume that it's true because it never failed. Whenever I inserted some numbers in there, it always worked. We want to be able to prove that this is true. So once we can formulate these rigorously in first order logic, then we can actually give the mathematical proof of these. And that's what mathematicians want. The business of professional mathematicians is actually doing logical proofs on and discovering these number theoretic theorems. For example, the Pythagorean theorem. When you learn geometry originally, you just learn how to use this thing and do some computations. But what the mathematicians want to do is they want to prove this theorem holds. And in order to do that, there's actually a couple of stages. One thing you have to do, for example, is give a rigorous definition of what it counts to be the sides of a right triangle. See, I just gave you like an intuitive understanding. I gave you an intended interpretation for this predicate, but we would want to define this predicate rigorously, and then we can actually pull off this proof, and you can do this. Notice when you define this, of course, C has to be the hypotenuse. So that when you give the definition of this, order, the arity of these argument places matters. How would you possibly give a definition, you might be wondering, of sides of a right triangle in logic in FOL rigorously? Let me just give you one example of a number theoretic property to show you how this goes, because it's straightforward. What about the concept of even? Like, let's say our domain is the natural numbers. Some of them are even, like 4, 6. Some of them are odd, like 5 and 7. Well, we can define this property actually in a really elegant way in FOL. We say for all objects in the domain, what is it for an object to count as even? So what I'm giving you here is I'm sort of, when I just say X is even in this way, I'm giving you an intended interpretation. But when I do it this way, I'm actually, I'm giving you a definition of what it means. And this is how you do it rigorously. And this is how I can start to do proofs on objects being even or not, and use this in other number theoretic theorems, like if X is even, then X squared is even, or these kind of theorems you would want to prove about numbers. So for all objects, they're even if and only if the following condition holds. There is some other object, or there is some object, maybe it's not another object, there's some object in the domain such that X equals 2Y. Now, what does that mean? Let's use an example. Like the number 6 is even. How do we know that? Because 6, there exists some object in the domain such that 6 equals 2 times that object. Of course, the Y in that case is the number 3. Or what about 4 is even? If and only if there exists some object like the number 2 such that 2 times 2 equals our 4. So if you think about it, this definition really does capture the concept of evenness on the natural numbers. And this is just one example. Notice, look at this. I'm not using anything except FOL here. This is just my identity relation. Number 2, this is just a name in my language for one of the objects in the domain. And indeed, you can define all these amazing number theoretic properties with first order logic, and then you can prove all of these fundamental theorems of arithmetic. Now, you might be wondering, can you do this for all the theorems of arithmetic? Those are sort of the metalogical questions that we want to know, and that's what folks go on to study in more advanced logic and more advanced mathematics classes. Let me say, I'm not going to focus on number theory and arithmetic here. I'm going to actually talk about a more fundamental aspect of mathematics called set theory. Set theory is really cool. It's because it's so simple, and and that makes it so elegant. It's beautiful in its simplicity. There's one fundamental concept to sets. Sets are abstract collections of things. They're just collections that have members in them. That is the fundamental concept of sets. And there's a way in which we can think about sets, since it's such an abstract and basic concept, as giving us a way of understanding all the other mathematical notions. Like, we can actually think of what it means to be a number as being a certain type of set. And what a function is it's an association from one set to another set. So all these other concepts, the concept of sets is so abstract and basic that you can use it to define all these other concepts from mathematics. And when folks do this, it's called first order set theory. And then you can try to prove theorems about sets. So we're gonna do that in this class a little bit, and I'm gonna show you some of the cool fundamental theorems about sets you can prove already from the amount of logic that you've mastered in this class. In order to do it, I just have to tell you I have to give you a definition of the one concept of sets, the concept of membership, or what allows us to define what sets are. And we'll start to use it a little bit in this video. So this video is just giving you the real basics about how we can talk about sets rigorously. In order to do it, and technically speaking, what counts as first order set theory is all we have to do is add one symbol to our first order logic. In addition to the identity predicate, we're going to add another binary predicate. So one other relation to our language, and the syntax is infix, just like the identity predicate. So what this says is A is a member of set B. Like A is in B, think of it that way. A is an element of B is another way people talk about it. And all we need for set theory is to add this one symbol to FOL, and then boom, we're off and running, and we can start to prove all sorts of amazing things. Let's talk about how we use this symbol carefully. if you've read the material, you should be able to figure these out. So pause your videos and try to assess each of these. Tell me which ones of these are true and which ones are false before going on. Okay, let's look at it. Now, what do these things say? What this says is the number 1 is an element of this set. And the way that we write sets is with these curly braces. There's actually many ways we write sets, but one of them is with these curly braces, and then you list the elements inside the braces, and you separate the elements with a comma. So this is the set containing the numbers 1 and 2. And yes, indeed, the number 1 is an element of that set. So this one is true. So these ones in blue are the correct answers. Now, is this thing an element of that? The answer is no, because this is a set right here containing the numbers 1 and 2. It is not an element of the set containing the numbers 2 and 1. Order doesn't matter in sets. So really, this set over here on the left is the same as this set over here on the right. And this set is not a member of itself. If this were the identity predicate, this would be true. But this membership predicate, this is false. This one is also false. This special set here, the circle with the bar through it, this is the empty set. This is a special set that has no members. And 0 is not an element of the empty set because nothing is an element of the empty set. The set has no elements. That's why it's empty. So that is false. Look at this one. Sets can be elements of sets. They just can't be elements of themselves. So here's a set containing the number 0, and here's a set containing the set containing the number 0. This is, syntactically speaking, this is all well formed. So once we start embedding sets in sets, you just have to pay very close attention to the scoping and where the braces close and open, and you'll be able to read it. So this set here is an element of this set over here. So this is true. Now, is the empty set an element of this set? This one is true as well. This might seem weird, but this is just a special symbol. It's like shorthand, a helpful way we have to refer to the empty set. But of course, we can also refer to the empty set with this braces, the list notation, by simply not listing any elements in it. See, when this brace opens and this brace closes, there's nothing in there. So this is another way of writing the empty set. So the empty set is an element of this big set over here. So that's why this one comes out as true. This one is not true because the empty set is an element of this big set over here, but the thing on the left is the set containing the empty set, and that is not over here. See, what's over here is the empty set, and then also the empty set, so that's just repetition. That's really the same thing. And then another element of this set is the set containing the empty set and a set containing the empty set. So this is, you have to be careful with the embeddings. The set containing the empty set is an element of this main set, but that doesn't make it an element of the main set itself. So being embedded in a set that's embedded in another set does not make you an element of the main set. I know it's confusing to hear that out. Let me say it again. Just because this thing here on the left is an element of something over here on the right, that does not make it an element of the main set. You can't like collapse all these. It's not like throwing everything in a bucket. So if it's in one of these sets, it counts as being in the main one. Rather, the element of, or the membership relation, talks about the direct members. And this thing is not directly a member of this main set. It's only sort of indirectly a member of it. Well, we don't want to talk like that. It's indirectly in this thing by being a member of the set, but that doesn't make it a member of the set. Okay, sorry if that sounds confusing to say it in words because it involves all this iteration or repetition. Maybe just seeing more examples. Maybe I'll do another video and add more examples of this to make it clearer. Let me talk about one other concept you need. So pause your videos and see if you can answer these. I've introduced a new symbol here, which you should be familiar with. I'm going to let you try to figure these out before I tell you what it is. Okay, that was your chance to pause your videos. The new symbol, of course, is this vertical bar, and this means something else in set theory, which allows us to talk about sets. We don't need this symbol in addition. This is not actually a primitive symbol of the language. This is the symbol that we use to talk about set theory. So this is not something we add to FO set theory the way that we add the membership relation. Just like we don't need to add the empty set in. This is, in a sense, shorthand, helpful terms we have for talking about sets. But the membership relation alone is all we need to rigorously define sets. So some of these don't have that symbol. This is, of course, the cardinality symbol, and it talks about the size of sets. So this sentence is true. The set 1, 2 is the same as the set 2, 1, because order doesn't matter. Sets are not ordered objects. although you can use sets to define ordered objects. This sentence is false. So the first one is true, the second one is false, because this is the set containing the number 1. Repetition doesn't matter. This is the set containing the number 3, but 1 and 3 are not the same numbers, so these are not the same sets. Now, the size of these things is the same, because there's one element over here, since repetition does not matter, and there's one element over here. So that's why the blue one is actually true, because once you add these vertical bars, now we're not talking about the set itself, we're talking about the size of the set. And two sets can have the same size, even if they're not identical sets, which is what the contrast between these two things illustrates. Okay, now this one down here is false, because the set, this thing over here, the set containing the number 0, the cardinality of this is 1, and that is not the same as this, as the empty set. But if you look at the cardinality of the empty set, that actually is 0, because there's nothing in here. The number of elements in the empty set is none, namely 0. So the cardinality of that thing is just the number 0. So that sentence turns out to be true. Now, the cardinality of the empty set, though, is 0. The cardinality of this set is not 0. You see, this set contains the number 0, but that means it contains something. It contains one element, namely the number 0. So there's one thing in this set. So the cardinality of this is 1, the cardinality of this is 0, and 1 does not equal 0. So that's why this final one is false. So what we've done in this video is we've reviewed some of the basic concepts of sets in order to talk about sets. We've talked about cardinality, we've talked about sets as collections of objects, and we've talked about the membership relation and what makes something an element of a set, which we define by that the membership relation. And this is all the machinery we need. We can now start proving some really important results about sets. Okay, thanks.